Hello everyone, good morning. My name is Rafal Jean-Gilles. I am the Field Application Sciences Director here at Engine Labs. I would like to welcome you and thank you once again for joining us for another webinar. So today's topic and title is going to be only on Uncle. So what Kevin is going to do today is kind of walk us through the unique insights that you can get by using the Uncle. And so what's really interesting there is that we've spent some time discussing features and applications and the unique things that you can do with the Uncle, but now it's going to be some perspective on exactly what makes the Uncle so unique among the options that you might have as you're looking to characterize your therapeutics. So if you have joined us before, you may know this already, but if you have not, we have a Q&A that's going to be at the end of the presentation. So please submit your questions down below, perhaps on top, depending on your layout, and you will see a Q&A option. And simply submit your questions, and we'll try to field as many of them as we can as we go through the Q&A queue that's going to be happening at the end. If you also have other questions, feel free to put them in the chat room. But once again, sit back and enjoy. And Kevin, the show is yours. Thank you.
All right. Yeah, thanks for that introduction. As Rafar said, the goal of this talk is to really zero in on where the difference is for Uncle and what really makes it special. So I have 3 or 4 different stories. Some are quite new, and so we'll take you through it and see what kind of questions come up. Okay, so let's get going. So as this bed shows us, having just the bare minimum really isn't enough. So only having one option to solve a problem doesn't leave you with any flexibility. But by having more than the bare minimum, you can get what you really want, which is, of course, options. So in the world of biologic stability, options mean the ability to solve problems faster and with less sample. So where you have a problem, having options gives you the ability to actually go investigate and figure out what's causing that problem. So that brings us to Uncle, which is, as we said many times, the multimodal all-in-one biologic stability platform. So it has options. It has 3 different detection methods: full spectrum fluorescence, static light scattering, and dynamic light scattering, that we can combine into 12 different applications that all use only 9 microliters of sample and let you take those samples through a wide range of temperature control. So we'll be looking at exactly what those 3 different detection methods offer that gives you very unique abilities to solve problems. That's across proteins, viruses, peptides, the wide range of the biologic space. So the first part of the Uncle's unique story is the uni itself. So the uni is our sample holder. It's an aluminum array. It has 16 9 microliter quartz cuvettes in it. So each one of these cuvettes is essentially a quartz tube where you pipette in your sample. It's held in there by capillary force, and then later you clip it shut with these silicone seals in this blue frame. Now, where that already starts out to be the unique part of Uncle is that your sample is sealed and you don't have to worry about evaporation. So doing anything like a long-term isothermal study, you're ready to go. It's no different than running any other sample, and you don't have extra steps where you're sealing with a film or adding extra silicone to expose your solution to different silicone greases. So that's great because already you know that your sample's only coming into contact with inert materials like quartz and silicone. In addition to that, it not only performs at higher temperatures, it also performs at lower temperatures. So it's something where you can freeze the uni and do freeze-thaw studies right in that same sample holder without any changes to how you would normally run a sample, which gives you really good comparability to your normal results. So when we take that uni and we load it in our Uncle, you can use up to 3 unis at a time, which means you're running between 1 and 48 samples, depending on what you need to do. And then Uncle is going to apply 3 different unique tools or detection methods to that sample: the full spectrum fluorescence, SLS, and DLS, like I talked about. And it will take that from maybe a thermal ramp from 15 to 95 degrees Celsius, or hold it isothermal at an elevated temperature, run something at room temperature, or maybe do a dramatically different profile, like a turret profile where the temperature cycles up and down to test out refolding of your protein. So for each one of our 3 different detection methods, we're going to look at a unique study and where Uncle provides unique value in solving your protein problems. So let's start with fluorescence. and talk about what's only available on Uncle. So for protein fluorescence, starting from the basics, we have 3 different amino acids here, tryptophan, tyrosine, and phenylalanine, and they all provide slightly different fluorescence behaviors. So where we'll be exciting with the 266 nanometer laser that will be absorbed by all 3 of these amino acids shown by the blue curve, which is their excitation wavelengths, and then they'll emit fluorescence shown by the green curve. So what Uncle's full spectrum fluorescence is detecting is the green emission behavior of all of the amino acids in your protein. So when you kind of sum up all of those amino acids that are excite and fluoresce, that's how you get to the total intrinsic protein fluorescence of your sample. As you heat up your sample, your fluorescence will change. That's the basic fundamental of how Uncle is telling you information about your protein as you heat it up. How that looks is much like this. So each one of these lines is a full spectrum fluorescence read at a different temperature. In this case, the samples start at a low temperature, and then as the curves decrease, that's increasing temperatures. And you can see about at this point, the peaks begin to shift to the right. So what's going on there is we're exciting with a 266 nanometer laser, a UV laser. Your proteins are emitting intrinsic fluorescence. Uncle is detecting the full spectrum fluorescence. And as the sample heats up, sample's unfolding and changing its fluorescence intensity and changing its average fluorescence wavelength. So what we'll typically do for an analysis of this is look at the BCM wavelength, which is sort of the center of mass of the area under the curve. So that might start at a lower numerical value, a lower wavelength at the start, but as things shift to the right, that BCM wavelength will increase. So we'll take a look at that in a couple of slides and a unique story on how that full spectrum fluorescence provides additional insight and data. But importantly, because we're gathering the full spectrum fluorescence on Uncle, you can actually use this to do both protein intrinsic fluorescence and a variety of dye-based fluorescence. So we'll have just a couple short examples on looking at SYPRO Orange, ANS, CPM, available in this presentation and in other materials. But the idea is that you can collect this full spectrum fluorescence, then analyze just the region that you want so that you could maybe use those proteins or dyes for fluorescence, but also ignore any kind of fluorescent buffer sample that might be present or any sort of contaminant that might be interfering with your signal. And like I said, when we have this full spectrum fluorescence, we can then analyze it in a variety of ways. Most of the talk will be looking at barycentric mean, which is that center of mass analysis, but we'll also have some results that look at area under the curve analysis and a few results that look at ratio analysis between 350 and 330 nanometers. Okay, so a typical result will look something like this. In blue, we have that BCM wavelength that I've spoken about for our protein, and as it unfolds, as temperature increases, we end up with inflection points that are melting temperatures. In this case, we have 2 melting temperatures for our protein. And then by gathering SLS data, which is going to be equivalent to shining a flashlight on a foggy day and seeing how much light gets scattered off your sample, that's going to tell us when our sample starts to aggregate. So in this case, we're gathering both fluorescence data and SLS data simultaneously. We can identify that the SLS data is increasing very near melting temperature 2, which tells us that melting temperature 2 is probably the temperature to pay the most attention to in this experiment. So that gives us both stability and aggregation data in a single experiment in a single sample in about 2 hours that helps us start to screen different proteins or different formulations or different conditions as we want. Okay, so the first story that I'll be looking at for full spectrum fluorescence is looking at a mutation in a protein construct. So conceptually, the idea is we have a protein, this red ribbon structure. We already know that it has 1 tyrosine inside of it. And we're going to compare that to a mutant where we've added a second tyrosine in the hopes that it would be change the structural behavior, the performance of this protein. We'll be looking at the stability as a means of understanding how this mutation impacts the protein itself. Okay, so when we run the sample, what we end up with is a little bit of a very, unclear result maybe. So on the left, we're looking at a traditional BCM metric where we have the 1 tyrosine result in blue and the 2 tyrosine protein in green. So we're seeing a clear red shift in the 2 tyrosine protein and a blue shift in the 1 tyrosine protein. That's, not that unusual until you compare it to the ratio example on the right, where we see almost the opposite behavior in this analysis. And usually these two behaviors they'll look similarly, although there'll be different amounts of signal and noise present. So in a ratio, you can expect slightly higher noise in that measurement, but usually you're going to see a redshift in the BCM means a redshift in the ratio. But now we have gone from a redshift, which is an increasing signal, to a flat signal. And likewise, with the 1-tyrosine protein, we've gone from flat to a blue shift. So that's pretty unusual, and I think that's something that merits more inspection to understand what's going on with our protein. So if we look at the full spectrum fluorescence, we actually get 2 clues into what's happening. The first is shown by the green arrow, which is the 1-tyrosine protein, or blue protein from the previous slide, actually shows a stronger tyrosine peak than the 2-tyrosine protein. So that's already pretty interesting because it's counterintuitive and not what we would have expected. So that's the amplitude of the shoulder here, 1-tyrosine having a higher amplitude than 2 tyrosines. The second surprise is that 2 tyrosines appears to show more of a redshift than the 1-tyrosine sample. That's something that we'll maybe make a note of and come back to in a bit. Since this is something that was confirmed by looking at our BCM data, where we did see a strong redshift by BCM analysis. So let's look a little bit further at what this is and what might be causing it. So analyzing UNCLE data, it's actually 3-dimensional data. So what we can do is we can grab that raw spectrum and put it into an Excel. And what we have here is wavelength along the x-axis, temperature along the y-axis, and intensity along the z-axis. So as we go backwards into the screen, that's going through increasing temperatures, and you can see how the fluorescence of those signals decrease. Again, we can see the green arrow where that difference in tyrosine appeared. So 1 tyrosine having a stronger signal than 2 tyrosines. But we can also see by graphing the data this way, is if we look at a contour plot, we can understand that that redshift actually appears to be a distinct behavior that isn't a smooth transition from the previous fluorescence peak of the protein. So that's shown by the blue arrow here, where we have 2 tyrosines, we have this additional sort of blob, we can call it, but that's absent in the 1 tyrosine protein. So that tells us that there's probably something unusual going on with this protein that's happening starting at higher temperatures. And indeed, if we start looking at the fluorescence spectra only for those higher temperatures, we can start to understand what that actually is. So in this case, we can take our 2 tyrosine mutant and pick out 1 fluorescence trace at a higher temperature and show that in green, and compare it to a result where we kind of investigated this signal in a separate experiment in yellow, where we're looking at just an IgG protein combined with some dityrosine that we've spiked in. So this starts to tell us what's going on here. When we've added a second tyrosine to our protein, what we've actually done is we've given it an ability to start forming dityrosine in our protein. So that both explains perhaps the quenching effect that's going on through the lower tyrosine signal, and explains that additional redshift behavior that we're seeing at higher temperatures that was unexpected when we compare it to our 1 tyrosine sample. So by using the full spectrum fluorescence of UNCLE, we're able to first of all see the difference between these 2 proteins. Second of all, investigate what's going on there and pick out some likely suspicious candidates. And third, actually identify the cause of what's behind all of this fluorescence behavior and help us understand structurally what we might need to change about this protein, whether that's removing that second tyrosine mutation or putting it in a different location of the protein, depending on what our ultimate functional goal of this is. Okay, so that's looking at a lot of insight that we can get just from intrinsic fluorescence. I mentioned full spectrum fluorescence can also be used to look at fluorescent dyes. So this is kind of a concept of what we're doing with that. In this case, we are probably exciting with our dye at 473 nanometers. I don't say probably because some dyes can excite at the UV laser. We excite at 473 nanometers, and we're going to measure the fluorescence at some other region in our full spectrum detection, in this case between about 500 and 650 nanometers. So in the first example, we can maybe have a protein that on the left has no tryptophan or tyrosine signal, so we're not going to have any intrinsic fluorescence. And indeed, exciting with a 266 nanometer laser gives us lots of SOS scatter, but doesn't give us intrinsic protein fluorescence. By adding a SYPRO Orange dye, we can then actually excite that dye and use it to understand when that protein is unfolding, as the signal will increase as that dye is exposed to hydrophobic areas of that protein. If we analyze that signal for the area under the curve on UNCLE, we can see an increase where the protein unfolds, and that will be our melting temperature. Another pretty interesting example that we can use our UNCLE's fluorescence capabilities for is to look at membrane proteins with the dye CPM. So in this case, we're actually using a model protein, which is bovine beta-lactoglobulin, which is special because it's going to have both tryptophan residues and cysteine residues. So that means we can look at both intrinsic fluorescence by monitoring the tryptophan, and we can look at the CPM dye behavior because CPM shows when cysteines get exposed to solvent, and it'll increase its fluorescence in response to that. So here we have just a quick look at how this protein is going to behave, going both from a lower temperature at 45 degrees Celsius to a higher temperature. We see the two behaviors that we'd expect. We see a decrease in the redshift in the tryptophan, and we see an increase in the CPM fluorescence. And then analyzing this behavior at both of those wavelengths indeed gives us a similar melting temperature of about 61 degrees Celsius. And I believe our last dye-based fluorescence example is actually from the world of viruses, where here we're taking an AAV capsid that can have multiple stability problems. In addition to aggregation, it can also sort of lose its DNA in multiple different methods. The first one is probably less surprising to people is as we heat it up, proteins, just like any other protein, will unfold and capsid integrity will be lost and DNA will come out of their sample. However, there's another stability sort of mode that's important to monitor, and that's if we heat up our sample as it gets heated up before the capsid proteins unfold, DNA will actually leak out of capsids. And so UNCLE can monitor that by adding a SYBR Gold dye and tracking how that signal increases as more and more nucleic acids are present, since SYBR Gold will have increased fluorescence in the presence of more and more nucleic acid. And the results of that kind of experiment look something like this, which there are other talks that are available that go more into the details of this result. But the basic idea is as we increase temperature, there's a little bit of a decrease since there's a relationship between temperature and SYBR Gold dye fluorescence. And then the headline is around 50 degrees Celsius for this AAV9 serotype. We see an increase in SYBR Gold fluorescence that continues until capsid unfolding occurs and aggregation starts to go out of control as measured by SLS. So this is telling us that SYBR Gold fluorescence is increasing at a much, much lower temperature than we would normally expect to see based only on capsid unfolding and aggregation. This is something that we've seen now with 4, 5, 6 serotypes, and every single one has a slightly different behavior and varies based on the buffer that it's in as well. So very important to understand since it actually shows DNA release well before capsid unfolding for proteins. And it's something that you can only see with full spectrum fluorescence using a DNA sensitive dye like SYBR Gold. Okay, so that's full spectrum fluorescence. Let's take another quicker look at the other unique areas that UNCLE provides unique value, starting with static light scattering. So the way UNCLE does static light scattering is sort of what I call real static light scattering, which is a right angle static light scatter. The laser source comes into the sample, and then we're actually measuring the scatter that bounces back out at 90 degrees using our full spectrum spectrometer. So this is a standard angle for static light scattering and allows us to actually see what light is being sort of hitting and interacting with particles in solution and then bouncing back out towards our detector. So because we're doing this very traditional light path, this allows us to get other metrics from that setup, such as B22 and G22 measures, which are indicators of protein-protein interactions and kind of really fast measurements of understanding if your sample might be prone or susceptible to aggregation. Another unique value of doing this right angle light path with SLS is that it actually applies across the whole concentration range. So it's sensitive to both 0.5 milligrams per mil protein, all the way up to the maximum protein range that Uncle can get to. Other ways of looking at aggregation metrics in a sample can use backscatter optics, which this is a way of shooting a laser at a sample, having it pass through the sample once, having it hit a reflective surface and pass back through the sample a second time. And then we can measure the signal attenuation after it's done this 2 trips through the sample journey. So the problem with this is that it's not actually a light scatter, it's a light loss metric. So there's no way to get your secondary metrics from it. You can't get your B22 and your G22 metrics from it. And it's only going to be something where you're measuring a decrease in signal intensity as your signal changes. The side of the kind of corollary to this is that it's going to be less effective at high and low concentrations. At low concentrations, you're going to have a very, very strong signal where only a little bit of noise is lost. And at very, very high concentrations, you're probably going to lose a lot of your signal and have a much less sensitive response. So with right angle SLS, you can actually get results that look like these across that whole concentration range. So whether you're working at the very, very lower end or all the way up to 350 milligrams per mil, which this is for an antibody candidate, you still get those strong SLS signals and can get aggregation data. And in this case, we can show exactly how to use that sort of information where we talked about earlier, getting different melting temperatures, and we're seeing where aggregation occurs in response to those melting temperatures. So with this protein that has TAG that corresponds very, very nicely to melting temperature 1, we know that we can pay attention to TM1 as the behavior that's driving aggregation. Or with trastuzumab, where we're seeing in this buffer the aggregation temperature near melting temperature 2. Or even for cetuximab, where we're seeing aggregation well before we identify any melted temperature, which tells us that we should probably pay attention to TAG as the most important metric in this case. So that's an example of how we can understand aggregation and melting temperature and start to look at all the different behaviors that happen for different proteins in different formulations, and then start screening conditions and eliminating the worst ones and advance only the best candidates further down our pipeline. So that's why we end up with data that looks something like this as we start to screen more and more formulations, both for unfolding by fluorescence and SLS for aggregation. And then we begin to plot them and understand, hey, which ones have the highest ones of these melting and aggregation temperatures. And the other metric that I mentioned for SLS, just to cover it quickly as well, is B22. So in this case, we actually deliver B22, which is based on static light scattering, and KD, which is based on dynamic light scattering. And the idea there is that if we take a time zero snapshot across a range of concentrations, then as we increase different concentrations, what we're going to see is how our proteins affect one another. If we put more and more protein in the sample, and our proteins are, have attractive interactions between themselves, then that sort of increased frequency of interaction will show up as a decreasing line here, which indicates attractive interactions. So what we're measuring is, in the case of KD, we're measuring diffusion coefficient. So things will seem to slow down as we increase the concentration. Or in the case of B22 with static light scattering, we're measuring Kc over R90, which is going to be kind of equivalent to 1 over molecular weight. So the idea is that as we increase the concentration of our proteins, then they behave like they're a larger molecular weight protein. 1 over molecular weight decreases. And then the exact opposite occurs if our proteins experience desirable repulsive interactions. And the idea here is if we test a sample at varying concentrations, and that's something we can look at and understand right away, do our proteins in this buffer have repulsive interactions, which is desirable, or attractive interactions, we maybe need to reformulate or reconsider our construct. If we look at an actual example of how this data performs with a real antibody, we can understand in 2 formulations here, we have very favorable repulsive interactions by B22 data. So that's a strong positive slope. And then if we add in arginine or sodium chloride, we have a more neutral slope telling us that these excipients are not desirable for this protein in this formulation buffer. So that's something that can give us an answer right away, and maybe we can, reduce the amount of long-term storage stability experiments we have to do to only these two buffers to understand which one of those two performs better. Okay, and lastly, DLS is another very unique opportunity at UNCLE. So having the ability to get DLS on the same sample as fluorescence and SLS is where UNCLE really shines, because it helps you to answer some questions about the quality of your sample and the quality of your experiment very definitively. So in this case, DLS, we can take either a single sizing measurement, sort of a snapshot, and understand at one point in time, what is our size and size distribution. In this case, we're likely looking at an antibody that has a Z average diameter very close to 10 nanometers. Or we can take a series of snapshots across a thermal ramp and understand when size starts to change in response to temperature increasing, say in different formulation buffers or with different proteins. So as we'll heat up a sample, we'll see a behavior that looks like this. So we'll start from a very nice monodispersed sample where we have a known Z average diameter and a very small polydispersity index. And as we start to increase temperature, we can see shifts in the Z average diameter and increases in PDI, telling us that the sample is getting more and more heterogeneous. We're having more and more aggregation present in our sample. And this is starting to be less and less desirable. So comparing that across different formulations tells us which formulation is the most resistant to these kinds of changes. So where we can apply DLS to our typical thermal ramp experiments is something like this. So where we have our lowest concentration antibody result that I showed earlier during the SLS section of this talk, we detect aggregation by SLS, and we can actually confirm that by looking at the DLS results before and after this thermal ramp. So before the thermal ramp, it was a very nice monodispersed antibody around 10 nanometers in diameter. And after the thermal ramp, we've confirmed and sort of quantified aggregation by showing this result in red, so that we say, yes, indeed, this antibody did aggregate, and it did aggregated to a pretty severe extent. However, it also helps us answer questions about the quality of our sample, maybe in circumstances where we didn't get the result that we expected. So here we actually have an example of a lysozyme where we're using it as, the customer was using it as a melting temperature control, where they saw melting temperature behavior that they expected. This was occurring at about 71, 72 degrees Celsius, and that was very much in line with what they expected from their sample. However, when they looked at SLS data, they actually saw no change. They saw no aggregation that was corresponding with their melting behavior. This is very surprising to them, and they kind of came to us and asked what was going on. And this is actually pretty easy to solve, because all we did was look over at the DLS tab and check out what the size of the sample was when they started their experiment. And we know that lysozyme actually should be a few nanometers in diameter, but in their case, lysozyme was well over 100 nanometers in diameter, not at this green arrow where it should have been, instead distributed well over to the hundreds and thousands of nanometers. And that's telling us that they're starting on globs of lysozyme. And so they actually are getting the melting temperature that they expect, but there's no aggregation behavior because their sample's already aggregated. Okay, so that's an example of how we can check out size and size distribution. And then here's another look at how this Z average diameter can change over time, where we'll also get a melting temperature, a size change temperature off of this experiment at about 70 to 73 degrees. So if we look at different formulations, I wanted to pull one more example in for this thermal ramp for DLS. We can look at IgG in different concentrations of arginine and understand how arginine sort of suppresses that change in size. And so we know that higher concentrations of arginine give us higher T sizes, so that we know that these formulations are more reluctant to aggregation. All right, so that's a look at the three large things that you can only get on UNCLE. So with fluorescence, you're actually able to see everything and get miss nothing. You'll get the full story of what's going on with your protein, and you get the ability to when something is weird, investigate and identify what's happening with your protein. With SLS, you get scattering, you get 100% sort of authentic light scattering, but you also get those other benefits of B22 and G22 information. And with DLS, you don't just check your sample that it's well behaved and high quality. You get to prove it by showing that there are no aggregates present and that everything is the size that is, that it should be. So all of this is, combined on one sample, only on UNCLE. So, that's how having, the full set of options can help you solve all kinds of biologics problems. So UNCLE's really more like this, which, if we're being honest, is the bed that everyone really wants at the end of the day. Okay, so now I think I'll pause and ask, what questions do you guys have for me?
Thank you very much, Kevin. Okay, so before we get to the questions, I just want to make sure I understood what you were saying. So essentially, the goal here was to demonstrate what's unique about the UNCLE, right? And so I tried taking some notes, and then I'm going to recap and let me know if I get this right. So small sample volume, right, 9 microliters, rather unique, and your sample is actually sealed, so there's no concern about evaporation there. So I thought that was quite nice. And so if I want to do long-term studies, the UNCLE is really nice for elevated temperature isothermal studies over an extended amount of time, for instance. Sounds reasonable?
Yeah,
right?
yeah.
Okay.
It's always that way too. You never have to compare between two different conditions.
Okay. Point number 2, fluorescence. I think from what I gather from this one, what's interesting here is that you're saying to me that the full spectrum allows me to basically look at any modality of unfolding for my proteins, right? So whether the redshift, blue shift, whether they seem to have unique features, you showed like a shoulder, I think. These are all unique things that we can do using the full spectrum that otherwise we will not be able to characterize. Is that sounds about right?
Yeah, absolutely. And even with the example that I showed, it's you would have reached one conclusion if you only had part of the story, and that conclusion would have been probably wrong.
Okay. And then the interesting thing I'm going to stop there is that I really love when you said real light scattering, I think, or something like it. I thought that was quite interesting. Nice way of putting it. But yeah, I think that's a very relevant point, right? And I think you kind of showed the impact that can have on the ability to assess different concentrations. So you have full dynamic range if you are doing true static light scattering. Okay. That was quite great. Yeah. I think that's the takeaway message. And of course, the benefits of DLS, you mentioned B22, KD, and all those other things. So we have received quite a few questions, so I'm going to not delay that and get going. I'm going to basically go in the order that I see from top to bottom. So let's see, the first one there is you mentioned SLS to obtain TAG. Why isn't back reflection a suitable technique?
So actually some of the time back reflection can get you the answers that you need, but it does struggle at high and low concentrations. So that's kind of where SLS is going to be really valuable, is if there's no aggregation, there's no, light scattering signal. So it's going to be very, very sensitive to small changes in aggregation or low concentration samples. And I've also showed data showing that it also works very well at high concentration. And then lastly, like we've been talking about, back reflection can't take you anywhere else. It can't take you to B22 or G22 information. Yeah.
Okay, makes sense. So basically you lose sensitivity at the low and high end of your concentration range, basically, right? That's kind of, okay, got it. Let's see, we have another one saying, I was talking to another vendor, who's quite interesting, who said that he had a higher data density than the UNCLE does. What is data density and how does it impact your data? Ooh.
Yeah, so data density in this context basically means how frequently you read the sample. It doesn't have much impact on your data. So kind of as a thought experiment, like think about it. Let's say you start from a sufficient data set and you start to interpolate a whole bunch of points between that sufficient data set. You haven't changed your result. You just added more points to your curve. You're not adding more information to your curve. So even though data density is actually measuring the sample and not interpreting, the story doesn't really change. Once you hit a sufficient amount of data, adding more points doesn't impact your data curve at all. So beyond that, it also means you're giving up on something. So instead of having a full spectrum fluorescence story of your protein, now you only have the time to get a limited data set of just a couple of wavelengths.
It's funny, as you were saying that, I was trying to think of an analogy, and bear with me here, but I basically came up with the idea of having like a black and white TV, that's at 4K, right? Versus having color, like a full, full color TV. Sure, you have really high definition, but you're really only seeing black and white, so it's really not all that useful in the long run, right? So I think I see your point there. Okay.
Yeah, you can always go from color to black and white. You can't go
Right.
the reverse easily.
That's fair. Okay, so can you comment a bit on why you do BCM instead of fluorescence ratio?
Yeah, so BCM, we actually like it because it makes use of our full spectrum fluorescence. So if we start from taking a large amount of data, which for our BCM is between about 300 nanometers and 430 nanometers, and analyze all of that data, then we have a really, really robust signal to noise ratio for every single piece of fluorescence. So it's no longer susceptible to little changes around 330 and 350 nanometers. It's looking at a large chunk of fluorescence data and analyzing it to come up with one wavelength number. So that's why we like it. It's basically a really good way of getting a strong signal to noise ratio.
But we can do fluorescence ratio if we need to.
Oh yeah, absolutely. Yeah.
Awesome.
Again, it's going from color to black and white, I guess.
Exactly. Good. Let's see. So there are some easier questions here. Can we find a recorded webinar somewhere after the seminar? So yes, so if you are watching this right now, if you're registered, you are going to receive an email automatically with the follow-up links if you need to. This will also be on our YouTube channel. So if you go to youtube.com/BloomChainLabs, you'll be able to access all of our webinars on demand. So feel free to look at them there. Otherwise, you can send us an email at info@unchainlabs.com. If you cannot find anything, we'll be happy to send that to you as well. Okay, let's see, some of the technical questions. What else we have? Okay, so I watched some of your AAV SYPRO Gold webinars. Is it possible to do this using intrinsic fluorescence? What other dyes can you do?
Yeah, so two questions there. Is it possible to look at AAVs with intrinsic fluorescence? The answer to that is yes. So AAV capsid, the capsid proteins are proteins, just, they have similar behavior to antibodies or anything else. You'll see a behavior if you look at intrinsic fluorescence where you get to a certain temperature and they begin to unfold and aggregate. So what we've just found in our capsid studies is that the SYBR Gold melting temperature occurs first. So we know that you can gather information about the DNA release, and then you can gather information about your protein capsid unfolding. But if you only look at protein capsid unfolding, you're actually looking at it at a maybe empty capsid or partial empty capsid, and it's not really a full story of the behavior there. So in terms of other dyes that we can look at, we have worked with SYPRO Orange dyes for protein unfolding, CPM for membrane proteins, SYBR Gold for DNA. We've looked at FITSI for just traditional fluorescence labeling. And we looked at ANS, which is similar to SYPRO Orange, in that it helps boost the signal from protein unfolding.
Okay. So staying with the dye question, there's a question by Sharon Pollock asking, are the dyes for DNA and RNA interchangeable? And have you tested RNA capsids?
So we have not yet tested RNA-loaded AAV capsids. I know that we're in talks to do that in some circumstances, but I can say that for SYBR Gold, it's actually sensitive to any nucleic acid. So it will fluoresce as nucleic acids are released from your capsids quite nicely. And then if you want to kind of change the story and be specific to one nucleic acid or another, then there are nucleic acids fluorescent dyes like SYBR Green 2 that would excite with our 473 nanometer laser and be specific to RNA.
Awesome, thank you. Let's see, so I know you've covered this a bit before, but why does DLS matter? Isn't SLS enough?
So DLS is, sorry. DLS is really important because it actually gives you a quantitative answer on size. So usually hydrodynamic diameter is the main metric that we're talking about when we look at that, but there's a large suite of metrics that come out of DLS results. When you look at SLS, it's actually a combination of a couple different effects. Usually there's a lot of parameters in those equations that are constants, but usually what's coming out of that is concentration and molecular weight. And so you can't disentangle those two parameters, but you can tell when aggregation occurs because you know that those signals are increasing, but you can't break that down into changes of concentration, say due to aggregation causing two particles to become one particle, or due to precipitation, or you can't break it down into changes in molecular weight. So that's why DLS adds value there, is it really that helps you understand the quantitative change in size, whereas SLS really gets you a very fast, sharp picture on when proteins are unfolding and aggregating, kind of resolved in time or temperature rather than resolved in size.
Got it. Thank you. Let's see. So someone is asking you, it looks like they cut this at the end, are there other options for DLS and DLS with heating? So what makes this unique to the Uncle? So I think one of the last slides, you were suggesting that the Uncle can do DLS measurements, but it can also do DLS with thermal ramp. And I think they're trying to assess why is that so unique, or why do you think that's something worth highlighting this?
Right. So with DLS with heating, so let's talk about DLS in general. So with DLS, most users will end up using it one of three ways. At room temperature as a quick snapshot, which is actually kind of nice because if you look at the concentration requirements and the volume requirements, Uncle sits at a very nice spot where it's the lowest volume and the lowest concentration that you need. So other samples that say use a 96 well plate require higher volumes. If you use a 384 well plate, they require higher concentrations. So Uncle is a really nice, you get both in the form factor for the consumable. So that's a reason to use it at room temperature. At elevated isothermal temperatures, you can look at DLS, fluorescence, and SLS all at the same time for the same sample. So that's getting you information on size and unfolding, and aggregation with SLS is a little bit redundant to the DLS at that point. But it lets you do that for up to a week of information. So this is a really nice way to, say, pick a temperature for a long-term storage stability study and pressure test it on Uncle at a small volume to make sure that you're not going too high or too low so that you're sufficiently stressing your samples. And then lastly, people will look at DLS over that thermal ramp, which is, what some of the results that I showed. So I think that's kind of where Uncle delivers unique value. It's sitting in a nice spot for volume and concentration, allowing you to do these samples with all three detection methods for up to a week, and then still getting you, ramping up to 95 degrees Celsius in the same consumable, which, most polystyrene plates are not going to be able to ramp up to 95 degrees Celsius.
That's a good point. That's a good point. Excellent. Let's see. So someone, Steve Sweetheart, said, pardon the ignorance, which modes are done simultaneously versus separately?
So no, it's a good question. So fluorescence and SLS are always gathered simultaneously. This just has to do with they're on the same light path, they're using the same detector. So if we're shooting a 266 nanometer UV laser at a sample, the detector is going to see the SLS from that UV laser, and it's going to see any fluorescence that's excited from that UV laser. Story's the same thing for the 473 nanometer blue laser, and you can do experiments where you're using either one or both of those lasers. And then with the DLS laser, that's a different optical path, and so that'll be sort of a different instance. And then in terms of measuring the same sample, you can actually read all of those detection methods with an isothermal experiment, kind of because you have lots of time, you can switch back and forth. Or for a thermal ramp experiment, you can read DLS at the start, read fluorescence and SLS, and then read DLS again at the end.
Good. Thank you very much. Let's see. Would you please also comment about the appropriate protein concentration for each of the techniques, fluorescence, SLS, and DLS? So I think this is more like a specs question. What is the concentration range of the Uncle, basically?
Yeah, so for DLS, what we'll typically say on our spec sheet is it goes down to 0.1 mg per mil of lysozyme, because again, because DLS is getting scattering based on sort of the total volume of your protein that's taking up. It matters both the size and the concentration range of the size and the concentration of your protein in solution. So that's the lower region for DLS. And then for the upper limit kind of depends again on the size of your protein. At a certain point, you'll get issues at high concentrations, but that's usually well into the hundreds of milligrams per mil. For fluorescence and SLS, the lower limit is 0.05 milligrams per mil for a antibody type protein. And then the upper limit is 300 mg per mil, again, for an antibody type protein. but that depends a lot on sample to sample. So you can go a little higher or lower depending on if your protein is especially well behaved or if your protein is larger than an antibody. Those are the kinds of considerations to think about.
Excellent. Thank you very much. Let's see. So protein concentration. Okay, someone said, as a follow-up to that, I guess, what protein concentration range would you recommend to get protein interaction, repulsion versus attraction? So I think this is the KD, B22, maybe G22 applications.
Right, right. So with KD and B22, the way that those assays actually work is at very, very dilute concentrations, there's not much interactions. So as you increase concentrations and start to get to around 1, 2, 3, 4 milligrams per mil for most antibodies, then you start to see interactions and you'll start to see the measurements that we're seeing go away from totally neutral. That's when we're capturing KD and B22 information, usually between about 2 and 10 milligrams per mil. For smaller proteins, it can be higher, up to maybe 20 mg per mil. And then G22 is actually another set of protein-protein interaction parameters that we can look at above 25 mg per mil that uses a different set of assumptions and again relies on static light scattering. And that will be useful all the way up into hundreds of mg per mil.
Awesome. So we'll take one more question, then we'll have to wrap this up. But I'm going to answer one of them, and I'll leave the last one to you. One of them is basically saying, can I view the recording as I missed part of the webinar? Again, if you go to our website, unchainedlabs.com, you'll find a way to access that. If you go to our YouTube channel, so youtube.com/unchainedlabs, you should be able to see it within 24 hours or so of this presentation. And then finally, if you have any questions about it, or if you still cannot find it, send us an email at info@unchainedlabs.com, and we'll be able to help you find the link, or we'll send you a direct link to the recording. Okay, thank you. And then let's see, the last question that we'll take live is going to be for Kevin here, going, aggregation seems to have a slow transition with temperature. How do you define the aggregation temperature, T-ag, and T-size? So I think this is more of a, how do you actually calculate T-ag or T-size? What does the software do in general?
Right. So with those parameters, what we're doing is we look at the first derivative, and then we pick a threshold on the first derivative. And so that's telling us where our samples, where our slope starts to increase. So for T-ag and T-size, say if it's a threshold value of 10%, then that's where our slopes begin to increase, and that's where our signal is increasing and our T-ag and T-size is indicated.
Excellent. Thank you very much, Kevin. So thank you to everyone who took the time to join us today. I'm going to again remind you that if you have any questions, I encourage you to go to either unchainedlabs.com. You can email us to info@unchainedlabs.com, or simply go to youtube.com/unchainedlabs. We're very happy that you could join us today, and we'll see you soon. Thank you. Thank you again, Kevin.
Thank you.